I'm Emmanuel Awarikabi. I'm a Ph.D. student. I'm working on waveguides for photonics application. And of course, we are in a photonics integration lab. Someone may ask, what is photonics? All we seek to do here is photonics has to do with generating light, transmitting light, and detecting it on the chip scale. It's very important because today, as you will agree, nobody wants a slow phone. Nobody wants a slow internet. Everybody wants very smart devices that can respond to their needs just on time. So this is going to revolutionize electronics because we are going to use it for various applications ranging from the internet. We need to be able to transfer data at a very fast rate because we are using light, and as you can agree with me, light travels at a faster speed, and with that speed we are going to encode data so that the data will ride at the backbone of light so that we are able to use it for various applications. Now again, you go to the hospital, conventionally maybe blood must be drawn from you, and then it goes through a lot of chemical analysis for you to be able to get the results. It takes a lot of time, but now we are using microchips, or we have what we call lab on a chip, where we are able to get a quicker turnaround time, where we get the results, and whatever is wrong with the person, we can be able to attend to the person right on time. And also in defense applications, we also need smart systems. And this is what is going to help us. And again, with electronics or other electronics, we have bulky systems. This one, we are looking at very small units. These small units, it means we are going to reduce power usage, power consumption. We are going to have smaller sizes, which everybody wants. Nobody now wants to carry any electronics that is so heavy. And this all feeds into that agenda.
My name is Xuehua. So this table is mainly for photoluminescence characterization. This table, we have two detectors. One is silicon and indium gallium arsenide. Another is like liquid nitrogen-cooled indium antimonide detectors. So basically, three detectors. It covers from visible range to mid-infrared range. And we also have this compressor. Together with this cryostat, it can lower the temperature to 10K. So help us with the photoluminescence characterization. So we work on germanium tin material. After the material is grown from the CVD lab, we bring the sample here. We do photoluminescence characterization to check the material quality. If this material will give us the PO result as we designed. If the signal is strong and the wavelength is as we designed, we will think this material is good. So we can do more about this material, like fabricate this material into specific devices.
So as part of my work, what I'm supposed to do is to transmit the light that is generated on a photonic chip, and that is the project that I'm working on currently. And so if you look at this setup by me, this is called probe station, and the probe station, we are going to use this probe station to be able to launch light into the waveguide that I'm working on, and also to know whether the waveguide that I have is working as it's supposed to be. The whole idea is to ensure that the light that goes into the waveguide, we are able to collect as much as possible out from the other end of the light. So if you see on the screen here, I'm measuring my waveguide, and you can see the waveguide on the screen, and you can see some distinct colors on the screen. The purple light is my waveguide that I hope to measure its properties, and this is the probe that I'm bringing the light with, and this is the other probe that I'm collecting the light with. So basically what I'm trying to do is to be able to know how much light is going through that waveguide, and with that I'll be able to know that if I use it for any photonics application, it will work as intended. So basically that is what I do. This setup that you see is called probe station, and it has arms, which 6 arms. Out of the 6 arms, we have 4 that is connected with fiber, and then the fiber is basically what we bring the light with. You know, the light is generated from a laser, and then the laser brings that light through these fibers into the probe station. Now you have an input probe that brings the light, and then you also have an output probe that also sends the light to the next unit that I want to work on. So at the end of the day, I need to be sure that the light that I'm bringing from the laser, I am detecting that same light and this Fourier transform infrared spectroscopy unit down here. So that is what it is. And you can see also here on top of this unit a camera that helps us to magnify whatever we have in the probe station, because we are dealing with very tiny devices and you need to be able to magnify it to be able to see exactly what you are working on.
So it also relates to our material. We add tin into the germanium. Germanium is an indirect material, but by adding tin into this germanium, we kind of tune this material to direct. Direct material has more efficient for photonic devices. So by adding different composition of tin, we can get the PO profile that corresponds to different wavelengths. So we design this. One more important function is to check one specific tin composition corresponds to one PO profile that corresponds to specific peak position. We want to check the peak position and also the signal the intensity of the signal. I like photonic devices, but I do some laser devices for my master. And for my PhD, I think there are still a lot of questions regarding semiconductor lasers I want to figure out.
I have benefited by learning a lot, because before joining this group, I didn't know anything about photonics. I knew it casually, but now I am able to understand what goes into the subject matter, and I'm also able to see how best I can improve upon existing systems, and that may be my contribution also in the field. So after my PhD here, what I hope to do is to be in industry where this knowledge learned will be applied and also to advance the field of photonics.